Welcome to our presentation about the adversarial robustness of Vision Mamba. So before we begin, we introduce Mamba. So Mamba is a new model architecture that brings together the best parts of transformers and recurrent neural networks, with Mamba models being parallelizable during training, so really fast for training, and linear time inference, which is even faster than transformers. So it's essentially the best of both worlds. And just like transformers, Mamba models have also been adapted to vision tasks very recently. And this is what's called the Vision Mamba model. And it's fairly unstudied, so no one has investigated the adversarial robustness of it, which is what we're going to do. So as a reminder, an adversarial attack is an attack where you slightly perturbate an image in order to make a model misclassify it. And the adversarial robustness of a model is essentially how susceptible a model is to this type of attack. And that's what we're going to investigate in this project. And the way we did it is we essentially calculate a bunch of robustness metrics for 3 different models in order to compare, namely Vision Mamba, Vision Transformers, and ResNet. And in order to do this, we first fine-tune them to the public figures dataset so that they are adapted to the same domain. Then we calculate the robustness metrics for the baseline models, i.e. before fine-tuning, and the fine-tuned models. Then we want to check some model adaptations to improve robustness and see how it affects the models themselves. So we do that by first doing adversarial data augmentation and fine-tuning the models again. So we include adversarial examples in the training in the hopes that it increases the robustness. And we also try blur preprocessing, where we blur input images before inference in the hopes that it essentially erases the targeted adversarial attack. And lastly, we take a qualitative view into the effect these additions have on the loss landscape and decision boundary for the models. So let's look at some examples. So to the right, you see the minimum perturbation adversarial examples for the ResNet model, i.e. these are the least affected images, or the version of the image that is the least affected in order to cause misclassification. And this would be for the Vision Mamba model, and this would be for the Vision Transformer model. So you can see there's a difference in how the artifacts look, with Vision Mamba anecdotally here looking like it requires some more intense artifacts to cause misclassification. But this is not enough. We need to actually quantify this, and we do this by analyzing robustness metrics. And that is what we can see here. I won't dive too much into this because first we don't have time, and also we didn't really get fruitful results. We suspect that our fine-tuning onto the public figures dataset harmed the inherent robustness of the models and in general their representational power, because we fine-tuned it on such a small dataset. So looking at these metrics, the only thing we can sort of conclude is that the blurring worked for ResNet only. Other than that, no results of note are present. We also take a look at some of the visualizations we created. And this was unfortunately also unfruitful. Again, this was mostly qualitative, but something one might have expected was that for the blur preprocessing that you would be able to see around the location in the feature space where the original image is located. There should probably, or there could have been, a robustness radius where it was safe to perturbate within before misclassification. But as you can see on the bottom right image, this was not the case. A small perturbation could lead us to numerous different classifications. So in the end, it is premature to conclude anything about the robustness of these models, but we think it warrants more extensive study. But in the end, it was a good learning experience for various modern tools for machine learning, and also we got some experience implementing cutting-edge models directly from source. Thanks for listening.